Good. So you are all welcome to this afternoon sessions of the HR analytics class. By the end of this session, the intention is to create a level playing field where even those that have not taken a statistics class will be familiarized with the fundamental assumptions that are used in deciding what analytical tool to use and which one to drop at some point in time. So this class is very, very important because we often come across students receiving data sets and going straight ahead to analyze it without really perusing to check whether indeed a superior analytical tool would have done justice to the entire analysis. And once this stage or this step is compromised, the implication is that all the recommendations that you are going to make for the targeted organization will also be flawed, because if you don't analyze the data well, you will end up interpreting it wrongly, making faulty recommendations out of it. So by the end of this class, we should be able to be equipped with the fundamentals to consider when you are selecting a particular analytical tool for your HR analytics. Okay. So inferential statistics. Generally, when we talk about inferential statistics, they refer to the field of statistics that allow researchers, and in this context, HR managers, to use a data set that they have on a selection of their organization to represent the entirety of their organization. So what that means is that depending on the size of your organization, you may not have that luxury of time to use all the members, the entire workforce in a given study or situation. Inferential statistics will grant you an opportunity to use just a selected few of it to make a case for the entire organization, which is a parsimonious and a faster way of getting to know the entire state of an organization. Now, inferential statistics also is considered to be a cornerstone in HR analytics, because if it is chosen correctly, it can help to determine whether HR decisions are evidence-based or they are misleading. And that is the point I was making initially, that if you just analyze any data sets available to you without considering whether they meet a particular assumption for a given analytical technique, then you are likely to mislead management, which is going to be a huge challenge for HR practitioners. So the fundamentals of inferential statistics, particularly for HR analysts, will help you to know whether the HR decisions that are being professed are evidence-based or they are misleading. Primarily, inferential statistics can be broken down into two main categories, and these include parametric tests and non-parametric tests. So think about it this way. If you are faced with the question on our screen, that is, if you want to test whether training improves performance, what kind of test will you use? If you want to test whether training improves the performance of employees, what sort of test will you conduct? Now, this is not a simple question to answer, because depending on the nitty-gritties of the various variables, which is the training and performance, the analytical technique may take a different direction altogether. So when you come across a question like this, don't assume, oh, as for training, we've been organizing it, and performance, so we know how the supervisors have been doing it. So we'll go for X and not Y. The reason why I'm saying you have to be very, very careful whenever you are confronted with such questions and the data set that comes with it is that training can be measured using different types of skills. Performance can also be measured using different kinds of skills. So the typology of the variable in terms of its scale of measurement will determine whether you are going to use a parametric analytical tool or a non-parametric analytical tool. And the hope is that by the end of this lecture, some of these confusions should be clarified to grant you the confidence that you can approach with some of these questions and data sets. So let's start with the parametric tests. When we talk about parametric tests, what are they? They are statistical tools or techniques. But these tools or techniques are several, and they are underpinned by a number of assumptions. So when we say we are running a parametric test or a specific parametric test, it means we are using a particular statistical technique which is accompanied by a series of assumptions. And what are some of these assumptions? The first assumption is that the data set that you are going to run is normally distributed, which means when you subject the data to a Cartesian plane, or when you draw it on the X and Y graph that we used to play with in our JHS and SHS. Remember that X and Y graph book that we were always working with? When you draw the data sets within that Cartesian plane, it should be normally distributed. It shouldn't be skewed towards the left or the right. And it should not be having a lanky stature. So that is the first assumption. Again, the variables that are measured should be at least on an interval or a ratio scale. So the key fundamental scale of measurement as far as parametric tests are concerned is that the variable, normally the outcome variable or the dependent variable, should be measured on either an interval or a ratio scale, which means if the variable is a categorical variable, then you cannot run a parametric test. If the variable is also defined on a nominal scale, then you cannot run a parametric test. So for you to go ahead with an analysis using a parametric test, first of all, ask yourself whether the data, the dependent variable can be measured on an interval or a ratio scale. And again, but not the least, is that the variance within the group should be homogeneous. And that is what we call homogeneity of variance. So if you go within the groups that you are comparing, for instance, if you are comparing HR department with accounting department, we are expecting that the composition and the background, normally the demographics, the age, level of education that you are comparing between the accounting department and the HR department should be homogeneous. The moment the groupings are uneven, then you cannot use a parametric test. So these are the basic assumptions about parametric tests. And for that reason, parametric tests can be used in analyzing several questions that may bother an HR practitioner, including a question on, does training improve performance scores? If you are trying to compare the performance scores before and after training, then you can use a parametric test that we call paired t-test. Do male and female employees differ in salary? If you are contemplating whether the differences in salary has something to do with the genderless, then you can use what we call an independent t-test to run such a data set. If you are also trying to predict productivity through engagement, using the question, does engagement predict productivity, then you can use linear regression. So parametric tests can assist us in analyzing and finding answers to several questions that may be bothering an HR person. So by summation, when do we use parametric tests? Based on what I've said so far, it is relevant to use parametric tests when the data set you are working with, particularly the dependent variable, is measured on either an interval or a ratio scale. Again, the sample size that you are dealing with should also be moderate to large, so that if it is a smaller sample size, then you will have to drop it and use a different but appropriate analytical tool. Then normality assumption must also be satisfied,
Sir.
which contains, yes, hello.
Sir, please, with a moderate or large size, so in numbers, can we say for maybe a sample of 50 and above?
Okay, so I was going to come back to these clarifications.
Okay, sir.
Depending on the school of thought that you are coming with, the argument is that if your data set or the sample size that you are dealing with is less than 50, then it is considered to be small. However, if it is more than 50, then it is considered to be large. But that depends on whether you are going to subject them to the Shapiro-Wilk null hypothesis testing or the Kolmogorov-Smirnov null hypothesis testing, which we will come to later on. But for now, the data set that you are dealing with, just have in mind that it should be moderate. And if you are dealing with just a single organization, then anything below 50 is considered to be very small. But if you are dealing with multiple organizations, then anything beyond 50 is considered to be substantial, even though some specific analytical tools may require higher sample size beyond 50 in order to consider as meeting the right threshold.
Okay, sir. Thank you.
All right. And so once these fundamental issues are clarified, as far as the question on when to use is concerned, and they are satisfied, then it can be applied to any HR metric that you may be interested in investigating on. So ranging from the performance scores, salary, sales figures, productivity index, and what have you, provided these metrics were measured using an interval or a ratio scale. And that is why the other time I was concerned about how, when you are designing your questionnaire, why you have to be deliberate about the way you measure some of these variables. Because if you make the error there and you come back, then you cannot just go ahead to be running a parametric test just because when you input the data and you run it, it is giving you some output. It doesn't work like that. Now, what about non-parametric tests? So non-parametric tests are the go-to avenue when the parametric assumptions are not met. And what I'm trying to say is that when you subject your data set and its characteristics to the assumptions of parametric tests, and they are violated, or the key ones are violated, then it becomes relevant for you to switch to the non-parametric test, because they also have a room to accommodate some of those inadequacies. Non-parametric tests normally assumes that the distribution of the data sets along the Cartesian plane, or if you like, within the X and Y axis graph, should not be necessarily normal. They assume that you can even have an abnormal distribution of the data set. And once the other indicators or assumptions are intact, you can still get relevant output or results that can inform and guide HR decisions and actions. It is also appropriate, or it can be used for ordinal or non-normal data, which means when the scale of measurement of your variable is either ordinal or any of the other things apart from ratio and interval, it can also accommodate it. Now, the non-parametric text from a statistical point of view is considered to be less powerful as opposed to the parametric ones in terms of its precision in the prediction of whatever it strives to test. But when you are not able to satisfy the assumptions of the parametric test, then it becomes necessary that you utilize the non-parametric avenues to address it. And so the same questions that we normally use a specific parametric test to address can equally be tackled with non-parametric tests, except that here the scale of measurement will no longer be a ratio or an interval scale, but an ordinal scale, which people normally characterize as a Likert scale. Normally, when you are measuring perceptions and attitude and all that. So if you want to compare a particular variable, such as satisfaction, across different departments, then instead of using one way ANOVA, the non-parametric vexing is what we call the Kruskal-Wallis test. The same can also be said about a situation where you are comparing whether gender and promotion are related, but you're also interested in the diversity of the genderless. You can use chi-square to draw a matrix to check that sort of comparison. And if you also want to check whether training change motivation levels, you can use Wilcoxon sign rank test as opposed to the pair T test that would have been used when we're dealing with a parametric test. So the job that parametric tests can do, non-parametric tests can also do it, except that the fundamental assumptions underpinning these two typology of tests are totally different. So anytime you are confronted with a particular data set, or you are planning on collecting a particular data, the fundamental question which should be guiding you is the sort of analytical test you want to run or you want to use eventually. Because such clarification will help you correct the scale of measurement for your various variables. So that if you intend to measure a variable like salary, then it becomes relevant for you to leave a space to let respondents write the exact salary that they are taking, instead of doing it on an ordinal scale where you will be giving them on an interval sort of arrangement, right? Now, it is also important to note that the type of data that you have is necessary but not sufficient to demarcate whether you're going for a parametric test and not a parametric test. So as I indicated, at least it should satisfy the interval or ratio scale. But under circumstances where the data set does not satisfy these features, then it requires you to go further to check whether the data set is normally distributed. And this particular question cannot be answered at the time you are designing your questionnaire, because we normally test the distribution of the data on the Cartesian plane after you've come back from the field and you are running your normality tests. So that one cannot be guaranteed. But it is still important that you run in order to determine whether you run a parametric or a non-parametric. Because if you violate the assumptions and you go ahead to do it, all the implications and the recommendations that are going to be on your data set will be flawed from the outset, and they will also be misleading. And that explains why a lot of publications are out there professing solutions to real world problems, but such solutions are not able to match up with the problems that exist in the world of work. Some of the reasons are simply because the analyses that were conducted were not subjected to some of these normality checks. They just assumed, oh, the data is there, so we can run it and see the numbers that will come up. And based on that, make some interpretations and recommendations. But it is more sophisticated than that. Now, this is a short question for you to ponder over, for me to see whether you've grasped what we are doing so far. So someone should volunteer to read, and as the volunteer is reading, I expect you to start putting together the answers to this particular question. So what I want you to be writing down is the type of data that will be used for it, whether the analytical technique will fall within the parametric or non-parametric, and which specific test, which at this point you may not know, but at least if you're able to get it, it's a plus. So one of you should volunteer to read for us.
A company wants to know whether its leadership training program improved employee engagement.
Discussion question training program. Hello? Hello?
Yeah, just one person should go on. Who is reading?
Discussion question. Improved employee on 1 to 5 Likert scale. Question 1, what type of data? 2, parametrics or non-parametrics?
Please, can you read it all over again, because I lost you at a point.
And then the 3 is which specific test? Thank you.
Tumesi, can you read it all over again? I lost you at a point.
Hello, sir. Hello.
Yes, please, it's clear now.
Okay. So please, you are saying something.
Yes, I lost you at a point. So can you read it all over again for us?
Hello.
Okay. Ewa, can you kindly read it for us?
Okay. Discussion question. A company wants to know whether its leadership training program improved employee engagement. Into bracket measured on 1 to 5 Likert scale, bracket close. What type of data? Parametric or non-parametric? Which specific test?
Okay. Now, let me give you about just 1 minute. Then we will discuss the type of data set that will be required, whether parametric or non-parametric, and which specific one. So I'm giving you like 1 minute. And by the type of data, I'm referring to how the variables should be measured. Good, the 1 minute is over. So who would like to share his view?
Okay, sir.
Okay, go on, Abuaji.
So, sir, with the type of data, I would go in for the ordinal data
Okay,
because the responses have ordered, and since it's a like a scale type of question, usually can be from strongly disagree to strongly agree. So I'll go
okay,
in for the ordinal data.
okay. Then what about the type of test, parametric or non-parametric?
So since or since I selected ordinal, it will fall under the non-parametric.
Okay, because
It's okay, so can be used for nominal or they are more flexible.
okay, so you said it earlier on. You even answered it without knowing what that you've answered. So because you are measuring it on an ordinal scale,
Yes,
that
please,
is
the
one
like
of
a
the
scale.
key assumptions of the non-parametric test. All right, now can you guess a specific test? Okay, that's fine. That's fine. So
Okay.
in fact, I'm impressed. I'm impressed with the contribution you submitted so far. Any other person? I want to hear varied views. Any other person? Yes, Francisca.
Yes, sir.
Uh-huh.
So, sir, the parametric or non-parametric.
Uh-huh.
I want to give another reason why it is non-parametric approach.
Okay.
So the word said it is because of the data is ordinal.
Yeah.
So I'm also saying that because the distribution of the responses can also not be assumed.
To
And
be
that
normal.
also be, yes, to be
Okay.
normal.
Okay. All right. Which is also contingent on the premise that the data was measured on a particular scale that is neither a
Yes.
ratio or interval.
Interval, yes.
All right. Yes, I want to hear more contributions. Beatrice. Is Beatrice here?
Yes, sir.
Beatrice, let me hear your voice today. What do you think?
So, I agree with Iwa that
You
it
agree
is,
with them?
I agree with Iwa, and the specific text I'm thinking is Wilcoxon sign rank.
Wilcoxon, okay. All right. One last contribution, then we will proceed. Mavis Abuaje. Is Mavis Abuaje present?
Yes, sir.
Mavis, let's hear you. What do you think?
Sir, as Vichy said, I also agree with Iwa.
Hmm.
I think the data is ordinal data. The type of data is ordinal data because the intervals between the numbers are not guaranteed to be equal.
Okay.
So, yes.
Okay. All right. So, the submissions that a number of you are all advancing is arguably correct. I'm not saying it is correct, it is arguably correct. And this will be correct or accurate when the number of items that are being used to measure employee engagement is just one. And the measures of leadership training program too is just one item. Please, are you following what I'm saying?
Yes, sir.
Who can just paraphrase all that I said to let me know whether you are listening or you are in your kitchen preparing some pepper soup, and later on you come back and say the whole show. Someone should just paraphrase the bit I just said about it being partly accurate. Hello? Yes, what?
Hey, your line keeps breaking. I don't know if I'm doing it.
Hey!
It's
Okay,
true.
Ewa heard me. Ewa, you go on and say what you were about to say. Hello, Ewa, are you there? Oh, is it only me or?
Sir, your line is breaking, so maybe if you can reposition
Your line
yourself.
was
Oh, really?
Yes, sir. I was saying
Wow.
it.
As for this one there, I think all of you are colluding for me to just say it all over again.
Oh, no.
Let me check my router. A moment. Is it better now?
Yes, sir, it's better. I can hear you now.
Okay. So I'm saying that the argument that a number of you are advancing in support of the idea that the data sets can be ordinal and it should also be analyzed using a non-parametric test is arguably true when the assumption is that the number of items underpinning these variables, which is the leadership training program and employee engagement, are just one. If you have only one items underpinning them, then the argument you are advancing can be accurate. Please, did you hear me now?
Yes, Prof, we hear you now.
Yes, sir.
Okay, then someone should paraphrase it for me, what I just said.
So, sir, if I understood you well, what you said is that everything Ewa and the other colleagues said is arguably correct because we are dealing with just one variables per the sample question we are handling here. Thank you.
Your choice of words, you have to be careful. What's it one variable per the choice of way? But I know what you are saying. Yeah, I think we are all on the same page. You remember in our previous sessions, I emphasized that anytime you are measuring a variable or a construct, try as much as possible to have a minimum of what?
2 or 3.
A minimum of three.
Three,
In
a minimum
fact,
of three, say.
a minimum of three is when you are going to run the analysis. But when you are going to the field, you should have more than three. And this is important because when you come back and you run your reliability analysis, some of the items or the questions will not be reliable. So you will keep dropping them until it gets to the reliable ones, which should be a minimum of three that you can use to run your subsequent analysis. So if you are dealing with a data set that measures leadership training program, employee engagement, and each of these variables have at least three items, then you can create what we call a composite variable out of them, which will be averaging the respective scores for employee engagement and the respective scores for the various items of leadership training program. The moment you average them, then it means you have converted the ordinal scale to a what? You've converted the ordinal scale to what? Oh, average is there.
To an interval.
To an interval. And that's allow you to now run a parametric test. Please, is the explanation clear?
No,
And
sir. Please,
based on this explanation, that is why questions like this, when you are approaching it, you have to be very, very careful.
Sir, can you please come again, please?
Which part?
On the explanation, please.
Which part of the explanation?
On the interval.
The interval. So
yes, please.
I'm saying that if the number of items that are coalescing together to measure these variables are more than one, then it means that you can sum them and find an average for the respective scores. And those ones can be appraised as closer to an interval scale. And so you can now move away from running a non-parametric test to a parametric test. But if you are using a global or a single item to measure leadership training program, employee engagement, then under such circumstance, you have no other opportunity of converting the ordinal scale to an appreciable one. So you will have to use a non-parametric test.
Okay.
And these conversions are normally done when we start, you start playing with the data in the SPSS or in R, because we don't work with the respective items. We rather aggregate them to create composite variables. And the moment you start composing them into how do you call it, into the composite variables, then it grants you the basis to now be treating them as an interval scale. All right. Please, is my screen visible?
Yes, Prof.
Yes, sir.
Yes, sir.
Okay, so this is an attempt to summarize the various types of parametric tests and their corresponding non-parametric tests that can be used when the assumptions of parametric analysis is violated. So for instance, anytime you are confronted with a comparison of the mean of one group to a known value. So let's say you are comparing the average salary in GCTU as an institution to the mean salary that is provided by Ghana Statistical Service. That sort of analysis can be conducted using a parametric test we call one sample t-test. However, when the assumptions of parametric tests are evaluated, and there are specific ones for one sample t-test, which we will look at later. Then the corresponding one is Wilcoxon signed rank test. Is it clear? The same can be said about whenever you are comparing means of two independent groups. So for instance, if you want to compare the mean of, if you want to compare and check whether males differ from females in terms of their performance, or maybe their attendance, their intelligence, their personality, then the type of parametric test that we can use is independent t-tests. And if the assumptions of independent t-tests are violated, you will use a corresponding non-parametric one that we call Mann-Whitney U-test. The same can be said also about a situation where you are trying to compare the mean scores of the same groups, normally in a pre-test post-test. So for instance, if you want to check whether, yes, the leadership training program, whether leadership training program can indeed improve performance of employees. Under such circumstance, it amounts to pre-post test because you can first of all collect the performance scores of the trainees prior to the introduction of the training intervention. And after administering the leadership training program for maybe 2 weeks or so, you go back and record their performance. Having gathered the pre-performance scores and the post leadership training program performance scores, you can now run a paired t-test to verify whether indeed there is a significant difference between the pre and the post leadership training program. Once the assumptions are violated, then you go by what we call the Wilcoxon sign rank test. Anytime you are dealing with more than 3 independent groups, then you cannot be using an independent t-test to run the analysis, but rather there is the need for you to use what we call one-way analysis of variance tests. So the analysis of variance is what we've abbreviated as ANOVA. For instance, if you want to compare whether there is a significant difference among the HR department, the accounting department, and the marketing department in terms of their performance, then we can run a one-way analysis of variance test to verify whether indeed there is a significant difference in their performance. And if there is a difference, you can go further with something that we call post hoc analysis, which we will look at later on. And that will let you know exactly where the differences exist, whether the differences exist between the HR department and the marketing department, or it exists between the HR department and the accounting department. The moment the assumptions of one-way ANOVA is violated, then you go by what we call the Kruskal-Wallis test, which is the non-parametric version of it. So the same can be done for correlation, regression, and so on and so forth. The point of this particular slide on your screen is to let you know that for every parametric test, there is a corresponding non-parametric test that can be go to when the need arises. And they all have their assumptions which you must comply before you adopt any of them. So the take home here is that if you are thinking of running, let's say, regression in your project work, you should be ready to demonstrate that the data set you are working with adheres to all the assumptions of regression. If you are contemplating of running one-way ANOVA or MANOVA, then you should be ready to demonstrate that indeed you are not just running it because it is available in SPSS and all your friends are running it, but you are running it because given the peculiar circumstances of your data set, it actually adheres to the assumptions of that. And there is a way of demonstrating all these assumptions, which we will be looking at from next week thereafter. Any questions so far? All right, let's make progress. We are now going to look at the general assumptions of parametric tests. And later on, we will zero in on the specific analytical tools under parametric tests and their respective assumptions. I have already touched on a number of these things, but in order for us to put them in their right perspective, that is why we are going to hammer on them again. So the first assumption that every parametric test should seek to satisfy is the level of measurement. The idea here is that the dependent variable or the outcome variable should at least be measured on an interval or a ratio scale. Now, assuming you are dealing with a data set that is not measured on an interval or a ratio scale, it is ordinal, but there are several items coalescing together to form the dependent variable. What would be the remedy here? Did you get my question?
Please come again.
Please let your attention be here so that we do not go back and forth. I'm asking that, ordinarily speaking, the level of measurement for any parametric test should be at least an interval or ratio for the dependent variable. And I'm asking, let's say your dependent variable that you are dealing with was measured on an ordinal scale. However, the number of items under that particular variable is more than 5, like you have enough. What would be the remedy here? Is the question clear now?
Sir, please, if it's a remedy, can you
So
please
how
break
will
it
you
down?
handle it?
Is it to use Chromback Alpha to take those that did not get 0.7?
No. So those ones are going to be done when you are doing the reliability test. But even after the reliability test, you still have several items, more than 5, but they are on an ordinal scale. How will you handle it as far as this particular assumption is concerned? In other words, are you going to say that because the scale of measurement is ordinal, then I'm not going to use a parametric test. I'll use a non-parametric test rather. Or what will you do?
Yes, sir. Please, I think you use a non-parametric test.
You use a non-parametric test. Why?
Because it's suitable when the data is ordinal.
Okay. It's suitable when the data is ordinal. All right. Any other contribution?
So a non-parametric test because the dependent variables are more than 5.
Not dependent variables. I said the items. So the questions that are coalescing together to measure the dependent variable is more than 5.
Yes, please.
Then you put it together to get a composite value, the mean value of it.
And then what will happen?
so that you can get a single figure.
A single figure, and then you do what?
Mean figure for the five items.
Then you do a parametric or a non-parametric.
Parametric still.
Exactly. Anyway, I've just said it less than 5 minutes ago. But mind you, the justification for doing parametric or non-parametric should not be contingent on one assumption, right? So that the moment it met the first one, they say, oh, then the rest you leave them. You have to test all of them. So assuming you test all of them, and this the measure that is deficient, the remedy to it is that once it is ordinal, you can create a composite variable out of it and use that average to go ahead with your parametric analysis. But if you're able to satisfy this measure, but the data is not normally distributed, the variation of variance within the various grouping is also not homogeneous, and all those ones are violated, then you cannot still go ahead with it. All right. Normality assumption. So the idea behind normality assumption is that anytime you plot your data sets, particularly the dependent variable, on a normal graph, which we call the Cartesian plane, it should be bell-shaped, normally distributed. So when we say normally distributed, this is what we mean. Have you seen that this one, is it U that is inverted on the line? That is the shape you should get whenever you test for the normality of the data. Anything far from this will mean that the data is not normal. Now, you can test for the normality by using, you can use QQ plots, you can use histogram, you can also use, depending on the sample size you are dealing with. If your sample size is small, which is less than 50, then there is a portion of the output that you can use to test your null hypothesis. And that is where you use the Shapiro-Wilk test. But if your sample size is large and you are doing a normality test assumption, then you have to check the Kolmogorov-Smirnov portion of the outputs. And mind you, you have to know which one you are using to report, depending on the sample size that you are dealing with. But at the end of the day, the distribution should fall within this that we have on our screen. It should not be skewed to the left. It should not be skewed to the right. It should not also be plateauing somewhere here, but it should be normally distributed. So if you draw a histogram to illustrate your data points on a Cartesian plane, you realize that it will fit within this particular bell shape that we have on our screen. Once you achieve that, then you have also satisfied the normality assumption. Then
can we use a table to present the normality test?
Yes, you can use the table to also present the normality test. In fact, you can the scores from the tolerance and tolerance can also be used to check normality of the data sets. And in fact, that may even be an easier way of determining whether the data set is normal, because that one, there is a threshold that you use to determine whether it is normal or not. Unlike the use of this Cartesian plane, wherein sometimes some of the drawings of the histogram may be moving a little bit outside the distribution. And so it becomes a close call for you to determine whether indeed it is appropriate or not. So indeed, you can also use a table to do that. Then homogeneity of variance. So homogeneity comes from the word homogeneous. Variances within the group or across the group are expected to be equal. Variances within the group that you are observing or across the group should be equal. What that means is that assuming you are comparing two or more departments, and these departments are uneven in terms of the variations across the groups, then it will be very, very difficult for you to do a comparison of their outcome, because from the outset, the groups are not the same. So you cannot expect them to be performing or to be exhibiting the same temperament. So that is the assumption of homogeneity of variance. And it is tested using the Levene's test. The Levene's test is also one of the outputs that will be generated when you are running when you are running independent t-tests and ANOVA. It comes with the results that you will generate. And there is a null hypothesis associated with it, which we will consider when we start doing the practicals. In fact, all these assumptions, particularly the ones that you can use tables to address, they come with a null hypothesis that you have to now test to see whether it is, you will reject it or you will fail to reject it. Now, independence of observations. This assumption also contains that the observations that you are trying to measure should not influence each other. The moment they start influencing each other, then you will not be able to generate their independent states. A typical example will be a situation where we are trying to check the effect of alcohol on learning, the effect of alcohol on learning. Now, under such an experiment, it is important that the participants are given only alcohol. The moment, and then we have a control group who will be receiving something that looks like water. And that is what we call a placebo. Now, the moment somebody in the control group receives both the alcohol and the water, then we cannot subject their ability to learn to the placebo. And the same can be said about those that are also in the experimental group. It is only alcohol that we expect to administer to them, not any other drug that can enhance their recall and ability to learn. So anytime we are trying to measure a particular construct and also extrapolate the data set for further analysis, it is important that we measure the variable as it is, not influenced by any other extraneous variable or any other element in the environment that has the likelihood of also influencing the outcome. And that is why it is important that whenever you are cleaning your data sets, duplicates, triplicates are dealt with, because the moment you maintain all those double entries, it is going to increase the average scores of one particular group at the expense of other. And that wouldn't be a true reflection of the temperament of the ones that you are observing. Linearity assumption. Linearity comes from the word linear. Linearity comes from the word linear. And the linearity assumption becomes relevant when the analysis is escalated to the level of correlation and regression. The linearity assumption contains that the relationship between the variables that are being observed should be linear, such that as one increases, the other may also increase or behave in a constant manner, constant but predictable manner. The moment the relationship between the variables is not linear, but maybe curvilinear, then you cannot use a parametric test. So anything other than linear relationship between the variables that are being observed should not be subjected to a parametric test. That is where you may consider a non-parametric version of it. So if you were going to run a Pearson correlation test, and you observe that the relationship between the variables is not linear, then you have to go for the non-parametric version that we call Spearman rank test. Okay. Absence of extreme or outliers. Absence of extreme or outliers. Who can explain in simple terms what an outlier means? In general parlance, when we say an outlier in a class, or an outlier in the society, an outlier in a given community, what does that mean?
They don't conform to the norm.
Exactly. An outlier can be likened to a deviant. So from a statistical point of view, when we say a parametric test should adhere to the assumption wherein there is an absence of extreme outlier, it means that there is the likelihood for some of the data points to be extremely high or extremely low. Some of the data points could be extremely high or extremely low. Now, once these data points are identified, it is important to deal with them. Other than that, they will distort the results that you are going to generate. And let me give you a quick example. Let's say we are analyzing a data set on the age of our respondents. And so far, the age that we are coming across is within the brackets of 25 to 45. An outlier or an extreme outlier will be an age which is, let's say, 80. Majority of the ages that we are obtaining is between 25 and 45. Now, all of a sudden, boom, a particular age shows up and it is 85. It is 90. That particular age, because it is extremely high, whenever we compute the averages, it will drag the lesser ones up and create a faulty impression about the mean age of the class. Please, is it clear? So how to spot some of these outliers? You can use, there are several avenues. The simplest one is what we call a scatter diagram or a scatter plot. And that one will scatter the various data points you have on a graph sheet, let me put it that way, on that Cartesian plane for you. And you see that the outlier will be totally detached from majority of the data points. So whilst majority of the data points may be centering within the middle of the graph, then there will be an extreme one at the edge of the graph, and that will be the outlier. So in order not to allow the power of the outlier to distort the averages that you are going to generate, such an outlier can be dropped, and dropping just one outlier will not harm the data set that you are dealing with. So you can spot outliers using scatter plots. You can also use the standardized residuals. Box plots can also help you spot some of these things.
Please, what about if we have two major outliers? Let's say in the example you gave, one was
Yes.
90 years,
If
then
they
we
are
have
two,
another 5 years.
in fact, assuming you have the data set you have is going into 1,000, and you have just 2 or 3 or 5 outliers, you can drop those outliers and then go with the main scores that are clustering within the normal distribution. Okay. So this is the sixth one, multicollinearity. So multicollinearity comes from the word multiple multiple correlation. And it's normally adhered to whenever we are running either simple linear regression or multiple regression. Now, the main idea behind any regression modeling is to predict an outcome using some independent variables. So you are using the independent variables to gauge the outcome of the dependent variable. And we call the independent variables predictors. If you have, particularly if you are doing multiple regression, wherein you have more than one independent variable, all striving to predict the dependent variable, then the check for multicollinearity suggests that the two independent variables should not experience high level of correlation, because and that is why these days the most preferred tool to be running multiple regression is the use of structural equation modeling, so that you are able to predict the outcome variable with the two independent variables simultaneously, instead of in SPSS where you may be doing the stepwise way of regression. You'll be entering them one by one. So what happens is that because the two variables may be highly correlated, the moment you introduce the second predictor, then it will shoot the relationship of the predictors with the outcome variable to an appreciable level. And you may end up assuming that, hey, indeed, my model is very, very strong. The predictors are very good in explaining the amount of variance in the dependent variable, which in actual fact, that may not be the case. You are experiencing high level of regresses because ordinarily the two predictors have high level of correlation. A typical example is a situation where you are trying to predict employee performance using their level of satisfaction and motivation. Using level of satisfaction and motivation. Conceptualization-wise, measures of satisfaction also collate together to determine whether a person is motivated. So the moment you start entering these predictors in such a model, you realize the R square will be going up, the coefficients, correlation coefficient will also be going up, and you may be assuming the effect size will also be going up. So you'll be assuming that, oh, these are very good predictors of employee performance. But what is actually happening is that you are using two predictors that are ordinarily highly correlated. So whenever you are doing regression, it is important to check for the presence or absence of multicollinearity. And we can do that using the VIF scores and the tolerance values, all of which come with the output when you run the analysis. For VIF, the threshold for determining whether there is the presence of multicollinearity is that the VIF score should be less than 10. It should be less than or equal to 10. But in a more stricter circumstance, some statisticians contend that we should subject it to a threshold of being less than 5. Okay. Any questions so far? So what we've done in the time being is to demarcate what it means when we say we are using or conducting a parametric test and what it means when we say we are conducting a non-parametric test. And we've also gone through some of the assumptions that are required to be met anytime we are conducting a parametric test. Now, the presentation I did summarize all the assumptions together, but it is important to note that every analytical tool has its own assumptions. So we are now going to do a step-by-step breakdown of the assumptions for the various parametric tests. And please, these ones, there is no easier way of learning it. And what I mean by there's no easier way of learning it is that you cannot commit it to memory easily when you read it like the way you are learning Introduction to HRM or organizational behavior. But there should be a deliberate attempt to internalize the various assumptions for the various analytical tools. So right from here, please, I will implore all of you to make your own notes from these slides in order to understand when to use what. Once you pick it very well from this point going forward, it is going to help you in the way you structure not only your questionnaire, but how you even analyze it when you come back from the field. And when you come for your thesis defense too, these are some of the simple questions that we are going to be asking you. So kindly take notes. So the first one that we are going to look at is one sample t-test. And it is also called the student t-test. It's called student t-test because it was designed by an authority whose name is actually students. And it's not because students like it a lot. Now, we normally use one sample t-test whenever an attempt is made to compare a sample mean to a known or a hypothesized population mean. An example could be a situation where we are comparing the average salary of students in this class to the average salary that has been presented by Ghana Statistical Service. If I average your respective salaries together, and I want to verify whether it significantly differs from the average salary that has been submitted by Ghana Statistical Service, then The go-to statistical analysis is what we call one sample t-test. So what are the assumptions of one sample t-test? It must meet the dependent variable should at least be measured on an interval or a ratio scale. Then there should also be independence of observation wherein there is no situation where one person's response is repeated overly in there. So there shouldn't be duplicates of responses. Observations must be independent of each other. Normality. So the dependent variable, when subjected to the Cartesian plane or the normality distribution population, it should yield a normal, it should come out as normal, especially in small samples. And so when you are dealing with small samples, that is where on the output, you check the Shapiro-Wilk portion of the normality output. But if it is more than 30, still there is a call for concern because the population that we are going to deal with, for instance, if it is the population of Ghana, then we are thinking beyond 25 million. So when you have a data set which is like 100 respondents, that is still not appreciable or closer to the population enough. So normally when they are giving you this threshold about what constitutes a small sample size and what constitutes a moderate one, you should be thinking about the population that you are going to generate the results to. If the targeted population is into millions, then a data set of about 200 respondents, 300 respondents may not suffice. So kindly take notes. Then there should also be absence of outliers, which you can check using the scatter diagram that I mentioned around. Then independent t-test, independent sample t-test. Now, this is different from the student t-test because this one seeks to compare the mean scores of two groups that are independent of each other. So if we want to compare the level of intelligence of males and females, then we can administer an independent t-test. If you want to compare the performance level or level of satisfaction of accounting department and HR department, then we can administer an independent t-test because the presumption is that these departments or these groupings that we are dealing with, they are independent of each other and they do not require, the presence of one does not impede or inhibit the outcome of the other. So for independent t-test, there is no known mean, but you will have to compute it based on the composites that you create for the various groupings. The first assumption is the level of measurement must also be, for the dependent variable in particular, it must also be continuous, which means either ratio or interval. Then the independent variable must be categorical. So like I mentioned, gender, where you can code it into 1 for male, 2 for female. Now, if you are dealing with only 2 departments, then you can code the first department as 1 and the second department as 2. And this is important because that is the language the model will understand. There should also be independence of observation wherein no participant appears in both groups. So you cannot be a male, you cannot be in the male group providing responses and also be in the female group providing responses. You can also not be in the HR department as their employee, but when it gets to the accounting department responses, then you go in there too. also provide your scores. The moment you do that, then you will be violating that independence of observation. Then, of course, normality must be adhered to, homogeneity of variance, which contains that the variances, the differences across the group should be equal. So if we are comparing males and females, the presumption is that their age, level of education, religiosity should be equal across the groups. It shouldn't come across such that the participants in the male group are fairly aged, while the participants in the female groups are baby boomers. When you have such a situation, then the distribution, as far as age is concerned, is not homogeneous. And the same should be said as far as the how do you call it? The variables that you are measuring is concerned. Then, of course, there should also not be extreme outliers. So if you are trying to test some of your hypotheses using independent t-tests, then the expectation is that you will have to demonstrate in your write-up that you have met all these criteria, and that is giving you the impetus to go ahead with the independent t-test. Pair t-test. Okay, so pair t-test originated from psychological studies that sought to study twins to verify whether indeed their behavior, personality, and the way they are exactly the same. And it was out of numerous pair t-tests in twin studies that they got to know the variations in twins, that we have twins types near there. The identical ones, you know them. What?
Identical
Siamese, and then
that's
all
physical
those
appearance.
things. So it was out of pair t-tests that they were able to get some of these characterizations of twins. And what it does is that it gets to compare the same subjects twice in a given scenario. So if, for instance, an attempt is made to measure your performance, then using pair t-test, it will require that your performance at the beginning of the year will be recorded and at the end of the year will be recorded. Then we can cross-check whether there has been a significant improvement in your performance within the year. So that is the logic behind pair t-test. It seeks to compare means from the same participants measured twice. And that is why we characterize them as pre and post measures. Alternatively, you can say repeated measures, because the initial measures of an employee's attributes, perception, or an employee's attitude is thereafter compared with a latter attitude or perception of the employee to verify whether, as far as the means are concerned, there is a significant difference that makes a statistical meaning. So if you are trying to do a pair t-test, then of course, you should be ready to compare participant scores before and after an intervention is introduced. And for HR practitioners, this is normally employed when, for instance, you want to verify whether a training workshop that you organize on the use of protective PPEs, personal protective equipments, has resulted in a reduction in accidents. Under such circumstance, what you normally do is that at the pre-level, you will measure the number of accidents that are occurring within a month. And then you will keep that record somewhere. Then you will introduce the intervention, which is the training program on the use of protect PPEs. So after the implementation of the training program, then you will do a post-test. That post-test will be an assessment of the number of accidents that are occurring in the organization. So the mean scores of the pre-test and the mean scores of the post-test will now be compared to see whether there is a statistically significant difference between the scores. That will be a typical example of the use of a pair t-test. It can also be used in a situation where you are trying to verify whether improvements in conditions of service can also enhance employee engagement. So you will now have to record the level of employee engagement at the pre-level. Then you introduce the factors or forces that the workforce are calling for as part of the conditions of service and implement. And after some time, you go and do a post measure of the employee engagement scores. So that is how you can use paired sample t-test to do your analysis. Now, the assumption that it is also interested in include the level of measurement, which must be continuous, dependence of samples, that is, observations must be meaningfully paired, the independence of the pairs, such that each pair must be independent of each other. So that is why you have to get a record of the pre-testing scores and that of the post-testing scores. The pre-testing and the post-testing scores demarcation will help you know whether indeed there is the intervention that you introduce is making a significant difference or not. Then, of course, normality assumption must also be met. That is the difference between the paired observations must be normally distributed on the Cartesian plane, and then absence of outliers. Now, can you tell me the difference between paired t-tests and independent t-tests? Who can tell me the difference between paired t-tests and independent t-tests?
So please, can I try?
Yes.
So in independent tests, you are usually testing between two groups. They are independent of each other, but you use two groups. But in paired tests, there's one group that the same group is used as the experimental group and the control group.
Excellent. Thank you very much for the explanation. Now, one-way analysis of variance. Please, the ANOVA you are seeing here stands for analysis of variance, but it's been abbreviated. Analysis, the AN stands for analysis, the O stands for of, then the VA stands for variance. So there comes a time or a point in time where the number of groups or groupings that you are comparing may be more than two. Under such circumstance, you cannot use independent t-test because independent t-test grants room for only two groups to be compared. The mean scores of two groups to be compared to verify whether they are significantly different. So in circumstances where you have three or more groups that are independent of each other, then one-way analysis of variance comes in because it provides an avenue for you to simultaneously compare the 3 or more groups with each other. For instance, if you are comparing you are interested in comparing the performance of students across GCTU, Ashesi University, University of Ghana, KNUST, then one way and over will come handy. But beyond the number of groupings, which normally is 3 or more, it is also important that you meet other assumptions. And what are they? The dependent variable, of course, should be measured on a continuous scale, which means either ratio or interval. And that is why the preamble I presented on the assumptions of all parametric tests, they were all saying whether either interval or ratio. So that one also runs through. Then independent variable. There should be divisions or categorical. There should be at least 3 different groups that you are trying to compare. And that's what we mean by independent variables. And each of the groups should be unique or different from the other one that you are trying to observe. Then independence of observation. So measures of the variables across the group should also be independent of each other. It shouldn't come across that one of the participants is attending GCTU, Legon, and Ashesi University at the same time, who is also filling the questionnaires across. If it happens that way, then we violated that independence of observation. And that is why normally it's important to go through the gatekeepers who can give you access to the correct respondents for your study. And of course, normality must be adhered to, homogeneity of the variance, and then there should also be no extreme outliers. Now, who can tell me the difference between one-way ANOVA and independent t-test, even though I have explained it in my presentation? Can someone tell me the difference between independent t-test and one-way ANOVA? Who wants to try?
Sir.
Yes, is that Beatrice or who?
No, Franca.
Franca.
Please, I think it has to do with the number of independent groups.
Okay. So
That independent t-test is limited to 2 groups, but the one we are over is 3 or more groups. So that's what
exactly
I
so.
think.
Yeah, you are 100% correct. And thank you very much. Apart from that, all the things that independent t-test can do, one way and over 2 can do it. Except that here the comparison is done along 3 or more independent groupings. So please, if you are trying, if one of your objectives is to compare across the varied departments that are available in the organization, compare mean scores across such variations, then you should know what to use now. Is it clear? All right. Correlation. We normally subscribe to correlation whenever the intention is to verify whether an increase in one variable or one construct may result in either an increase or a decrease in another. So essentially, the essence of running any correlation analysis is to measure the direction, whether they are increasing or decreasing, and the strength of the relationship between two or more variables. But if we are conducting a parametric test, then we become interested in what we call the Pearson correlation analysis, which emphasizes on the use of continuous variables. Having said this, the assumptions underpinning correlation, particularly the parametric and the Pearson one, is that the levels of measures should be continuous for both variables. The levels of measurement should be continuous for both variables. And that there is also an explicit assumption of linearity between the two variables that are supposed to be related. So you have to test that assumption to verify whether indeed there is a linear relationship between the two variables that are going to be observed. And thereafter, of course, normality of the data set. The data set should also be approximately normal, which means it should be properly distributed along the bell-shaped curve. And homogeneity of variance, which is also known as homoscedasticity. The idea behind homoscedasticity is that the variance of one variable should be constant across levels of the other. There shouldn't be a situation where as one particular variable increases, then the other one starts misbehaving. So the behavior of the independent variable, under correlation, we normally don't. I'm traveling road my network. So the issue about homoscedasticity is just as what we learned as far as homogeneity of variance is concerned, and particularly in correlation, we don't demarcate one variable as the independent while the other is the dependent, because we are not trying to do a prediction here, but we are trying to strike whether there is a linear relationship between the two variables. And the expectation is that changes in one of the variables should be constant across the levels of the other. And that is what is going to give us that linear relationship. If changes in one variable fluctuates across the other levels of measures, then we are violating the homoscedasticity principle, or the homogeneity of variance principle. And we are entering into another concept altogether that we call heteroscedasticity, which we should not violate. So as much as possible, an attempt should be made to achieve homoscedasticity in order to run a parametric or a Pearson correlation test. And finally, outliers should be dealt with. Then regression. Okay. So unlike in correlational analysis, where an attempt is made to estimate a linear relationship between two variables, in regression analysis, particularly simple linear regression, an attempt is made to estimate an outcome variable using the independent variable, which we characterize as predictors. So what I'm trying to say here is that in regression analysis, an attempt is made to predict the dependent variable using the predictors or the independent variables. And there is an expectation of causation within this relationship because we are able to trace the explanatory power of the predictors to the dependent variable, unlike in correlation where the fixation was only on the relationship and the direction. So the assumptions underlying linear regression include that of the levels of measures, which cuts across that it must be continuous, and also the linearity assumption between the independent variable and the dependent variable should also be there. Then independence of errors, which means that the residuals or the error terms that are observed must be independent of the predictors. And you can test this by using the Debye-Watson statistics, which normally come with the outputs of the regression analysis. Then, of course, the homoscedasticity, wherein we expect the residuals of the various estimations to be constant across all predicted values. And normality of the residuals, which are also subjected to the Cartesian plane to see whether it is normally distributed. And there should be no extreme or influential data points, which we characterize as the outliers. That is simple linear regression. Then in some social circumstances, attempts may be made to predict a dependent variable using more than one independent variable. Under such circumstances, you cannot use simple linear regression. You have to make reference to what we call multiple regression. So multiple regression is normally utilized whenever the HR analyst is trying to predict a particular HR outcome, such as employee performance, using several independent variables, such as their attendance, the salary that they are earning, the number of training programs they've participated in, their level of education, and all that. If HR analysts try to model the predictors of employee performance by using more than two independent variables or predictors, then the most appropriate analytical tool is what we call multiple regression, because this grants room for several predictors to be modeled and bundled together to verify the amount of variance in the outcome variable that they are explaining. Having said it, the various how do you call it? The assumptions that characterize simple linear regression are the same ones that are also considered when we are doing multiple regression. Any questions so far? Any questions so far? All right. If there are no questions, then this is where we will bring the theoretical aspects of the HR analytics to an end. And from next week onwards, we will be doing more of the simulations and more of the practicals.